So, welcome to my presentation of proof 1.1, where we are going to learn more about calculating variance. It's a three-part proof, and I guess I'll jump right into it. So, part A asks us to show that variance of x is equal to the expected value of x squared subtract the expected value of x all squared after you take the expected value. So we know that variance is actually defined as the expected value of x subtract its mean or its expected value, write it as expected value of x and that's that squared. So the expected value of the squares. So we'll start by just expanding what's within here. So that is equal to the expected value of all this expanded, which is x squared subtract 2 x expected value of x plus the expected value of x all squared. Now, by the linearity of E, we can break this up. So we can say that expected value of x squared. Now notice that 2, of course, is just a number, but E of x, the expected value, the mean, is also just a number. So we can pull that out of our expected value and say, that subtract 2 expected value of x expected value of x plus expected value of our last term of the expected value of x squared. So actually, notice that the expected value of x squared is actually just some real number, and the expected value of a real number is just the number. So this term we can actually write as just the number that it is expected value of x squared, which is just what's within this expected value here. Okay, well notice E of x times E of x is just the expected value of x squared, so minus 2 expected value, it's an E, of x all squared. And here we just have our expected value of x squared. Well, 2 of something plus 1 of something is just 1 of the thing, so we end up with what we wanted to prove, which was that the expected value of x squared in the parentheses subtract the expected value of x all squared. Well, that's just equal to the variance of x. So we've proved the first part. So I'll just try to move some of this away. Move this out of the way, scroll up, scroll up. So we can move on to part B. So, part B asks us to prove that the variance of some number a times x plus some number b, this is what we want to show, is equal to a squared variance of x. So how do we show that? Well, let's work from our, not from our definition, but rather from what we just barely proved in part A, that the definition of this random variable, the whole thing, which is ax plus b, is going to be the expected value of the square of ax plus b. And that's a parenthesis. X plus b squared. Subtract what? Subtract the expected value of the random variable all squared. Ax plus b squared. So we'll expand this out, much like we did in the last part, to be expected value of a squared x squared plus 2ab x plus b squared. That is a plus symbol. And on this side, we will use the linearity of the expectation operator to break that up a bit. So subtract a expected value of x plus the expected value of b is just b, because b is just some real number, plus b, and of course don't forget that we are squaring all of that. So grab some more real estate here. by scrolling up. So again, for this term, we'll use linearity. So we get a squared expected value of x squared plus 2ab expected value of x and b squared is just a real number, so of course we can break this up term by term, and then the expectation of a number is just a number, so plus b squared. Then here everything goes and subtract everything that's here, so that's going to be a squared expectation of x all squared plus, what is that, 2ab expectation x it's an a, b, expectation of x. Don't know why I put this second set of parentheses around that, but it doesn't matter. Plus, then we just have b squared left. So, get a new color here to make this a little bit clearer. What do we have? So, plus b squared, subtract, because this will subtract everything here in the parentheses, so subtract b squared. So those cancel, which is nice, and that was actually a plus symbol, so I didn't get written very well. But plus 2ab expectation of x, subtract 2ab expectation of x. Well, something subtract itself is just 0, so everything there cancels out. And what are we left with? Well, factor out an a squared, and we are left with a squared, because we're factoring that out. Expectation of x squared, subtract the expectation of x all squared. Well, this looks familiar. This, everything I put in this curly brace right here, we proved in part A that that is actually the variance of x. So there we have it. We have shown that, remember, all of this, starting, way up here, was a variance of ax plus b. Come back down right up. We're clearly here. So this is the variance of ax plus b is equal to a squared times the variance of x, which is what we wanted to show. So I'll put a little box here to show that we have proved the second part as well. And I will grab some more real estate before we move on to part C, the final part of this proof. And I'll grab a new color, this fuchsia or whatever it's called, to do this proof. So part C asks us to Haven't been writing want to show. I like to write that though to remind myself that I haven't proved it yet. It's what I want to prove. It's the goal. That if x1 and x2 are independent, I use this orthogonal sign as shorthand for independent, that if those are independent, then the variance of the sum of those two random variables is the sum of the variances. So that implies that variance x1 plus x, sorry for the sloppy handwriting here, is the variance of sum of the random variables is equal to, I'll write it down here because I'm running out of space there, the variance of each one of them added to the other. Variance of x1 plus variance of x2. So this isn't true in general, but we're showing that independence implies this. So grab a new color, grab some space, and we will work from variance of x1 plus x2, and then hopefully make our way to this. So we've shown, first in part 1, that in fact is equal to the expected value of the square of x1 plus x2. So it's just a sum of two random variables is a random variable. Subtract the expected value of random variable, everything squared. So, well, we will expand this out a bit. I will start by expanding this guy. So that is equal to the, and we'll do linearity at the same time in this step. So expand this and use linearity here to save some space. So expected value of x1 squared plus 2 expected value of x1 times x2 plus the expected value of x2 squared. Okay, grab a new color for our second term here. So we are then subtracting from all of that. Put parentheses around this so I don't have to mess around with the subtraction symbol yet. So use linearity here, so this is just expected value of x1 plus the expected value of x2, everything in parentheses, all of that we are subtracting squared. So now what else do we need to do? So still need to expand this out so we get some nice cancellation, we hope. Grab a new color, so here, actually I'll do it like this. So all of this, just that term, is equal to the expected value of x1 squared plus 2 expected value of x1 times expected value of x2 plus the square of the expected value of x squared. Not x squared, x2. Misspoke there. Squared. Good. So that is, remember, we are subtracting all of these things. So I will demonstrate which things cancel out here. So we have, recall. So this is where independence comes in. We haven't used independence yet. We still need to use independence to make this work. So I will actually, don't have any more space there. So just recall that independence implies non-correlated, uncorrelated, which implies, so basically E x1 x2 equals E. So if you have two independent random variables, then the product of the random variables, the expected value of the product of random variables is the product of their respective expected values. So based on this, we know that that guy cancels with this guy because of this. And now we just have 4 terms. This guy, this guy, this guy, and this guy. And we will rearrange a bit. So so our first term up there, expected value of x1 squared, taking that from here. But now I will take this term, which we are subtracting, subtract expected value of x, oops, come back here, 1 all squared. Change colors here for the second 2 terms. So then we have the expected value of the square of x2. So plus expected value of the square of x2, and then subtract this term, subtract the expected value, the square of the expected value of x2. Well, by what we proved in part A. That's coming in handy again. This part is just the variance of x1. And this part is just the variance of x2. That's the sum of these, so all of that is equal to that. So we have the variance of x1 plus the variance of x2. Well, don't forget where we started. All of this is equal to the variance of the sum x1 plus x2, which is in fact what we wanted to show. So I'll come back down here and finish off this proof with our little square. See you in the next video.